Hello everyone, welcome to the spring semester, fourth semester of your Geomatics program, and to the course GEOM203 Advanced GNSS Surveys and Applications. So we'll begin today by going over the course outline so we understand what we'll be discussing and learning about in this course. We'll quickly go over the assignments, and not in great detail, but at least macroscopically in order for you to understand what exactly we'll be looking at. So the course description states that our studies will focus on developing a more advanced understanding of how GNSS works, specifically looking at now positional solutions. All right, we'll understand the signals that are being broadcast by the satellites, how we can use them to solve our positional problems, and we'll study the use and limitations of modern GNSS hardware and software. We will use and develop troubleshooting approaches to common GNSS problems, and we'll study modern approaches to positional problems. So as you can see here, the first thing is that excuse me, there is a 20% weighting for this course based on the amount of participation. Attendance is one, your participation in course discussions and things like that. There'll probably be some discussions that are posted online. There will be an online component to this course once again. There are 4 assignments designed for this course, and there will be a final exam. Possibly again take-home final exam that you work on at your own, covering kind of the last week. Then again, this is condensed into 6 weeks, so we get through a lot of information very quickly. So it's very important for you, the student, to be prepared for that. It's a little bit different than the other semesters, and you need to make sure that you're keeping atop of your homework, because there will be homework. Not assigned homework, but you're going to have things that are going to be due in a handful of days, all right, in order for you to stay on top of your studies. So the learning outcomes, pardon me, one step back, so the learning resources. The Hoffman-Wellenhoff book, which you should currently possess. It was the assigned book for your second semester Intro to GPS course. I have an exhaustive set of lecture notes that are kind of mishmashed from a whole bunch of different resources, but as your overall resource for this course, the Hoffman-Wellenhoff book is what's selected. Also, there is relevant information on how GPS works and some of the other things with regards to in Galani and Wolf. I think it's, or maybe it's still Galani and Wolf, the Introduction to Surveying textbook. The learning outcomes are analyze the fundamental principles of satellite positioning, analyze methods to mitigate the effects of GNSS signal obstructions, identify the key components related to GNSS carrier phase ambiguity resolution, perform a small GNSS control survey. So we will be trying to hit on some of the practical side, collecting some data, using it for our assignments and things of that nature. Okay, but again, this is not a field course. This is largely a theory course, but we will try to be supplementing the theory with practical applications as well. We'll compare precise point positioning, or triple P, versus static GNSS methods. We'll identify the key concepts related to network GNSS. So that might be a new concept for some of you. We're going to use an active GNSS network system. We're going to demonstrate real-time kinematic troubleshooting techniques. The troubleshooting techniques obviously depend on the equipment that you're using, so we're going to keep this fairly generalized, so we understand largely what the configuration settings are. And the configuration settings are going to be fairly common terms, say like RTK format or correction format, for example. So if you see those terms, you understand what they mean. And this, by having that knowledge, you'll be able to troubleshoot communication and configuration problems with theoretically any GNSS equipment. We'll perform a kinematic post-processing survey. So that's what PP stands for, is post-processing. And we will examine the relationship between grid and ground reference surveys. So again, just by going back to our understanding of coordinate systems, ground reference surveys using GNSS, grid or mapping surveys using GNSS, and ultimately geodetic surveys as well. That's the inherent coordinate system of GNSS. So that's the synopsis of the course, and today we're going to jump right into lecture number 1, which lecture number 1 is looking at the fundamentals of satellite positioning. So quick first, we're going to go through the history of GPS. So in 1968, the United States Department of Defense. That's what DoD stands for. All right, so DoD is Department of Defense, specified new requirements for locating its military forces worldwide. The concept of Navstar GPS was approved in 1973. GPS built on existing positional concepts. One was Transit, which was another satellite-based system that the U.S. Utilized. It was Doppler-based. Maybe in an upcoming section, when we talk maybe about network GPS, we'll do a more exhaustive discussion on transit and how it worked. Initial testing for GPS was done in New Mexico using pseudo satellites, okay, which were positioned on the ground, all right, where aircraft with prototype receivers were tracked. So it's kind of the reverse of how it is today. The quote unquote satellites were on the ground, and then there was a moving platform or moving receiver, and that was utilized to study to make sure that the signal structure worked and things like that. The first prototype satellite for GPS was actually launched in 1978. All right, so it is a system that has been around for a very long time. Okay, at least the ramp up, the concept, the proof of concept, and things like that for GPS have been around for a while. The first commercial receiver was the Stanford Telecommunications receiver, and it cost about $150,000. And today it would give you, I guess, kind of equivalent of the positional accuracy of, say, an inexpensive recreational, traditional Garmin or Magellan or something like that, or even your mobile phone would give you about the positional accuracy of close to that. Okay, now the system has evolved since obviously these early days, and the natural ability for the system to produce more accurate positions is obviously increased today. But nonetheless, you can kind of think of it in that term. The system cost more than $6 billion. Now that's a very, very low number. This is obviously some initial stat for what the system was planned on costing. Today, every satellite that's launched costs, hundreds of millions of dollars for the whole development of the satellite, the launch costs, everything like that. So this number would be substantially increased, and we're going to view a website here, kind of the official civilian website for GPS, and we might be able to get some more information on that. Two important dates to note with regards to GPS history is the initial operational capacity, or called IOC, was released to the public or stated to the public in December of 1993, with full operational capacity, FOC, coming, again, released to the public in July of 1995. It actually occurred earlier in late April of 1995, but these important time periods state or specify the states of GPS. So the initial operational capacity, meaning that there was enough satellites in orbit, they're producing signals that could be used to perform positional, surveys and answer those types of questions. However, it kind of wasn't green lit when initial operational capacity was stated. So it's kind of like a use at your own warning. With regards to that. Once full operational capacity occurred, there was specific guaranteed levels of accuracy for positioning as well as timing as well, when we'll talk more about timing coming up. So you can kind of think of full operational capacity as being when GPS, the entire system, was green lit. It had 24 active operational satellites in orbit. It was producing, the levels of accuracy, positional accuracy, and timing accuracy that were desired, and hence away the system went. So GPS characteristics: the average constellation was designed for 24 satellites. I haven't updated this slide in a little while, but we can look at this more closely for what it is today in 2015. But I think it's around probably the 30 to 31. I don't think it's still currently at 32 satellites, but again, they're launching new satellites and decommissioning satellites kind of all the time. So it's going to be right around, let's just say, that 30 satellites that are currently in orbit and we can utilize. There are 6 orbital planes. All right, the nominal altitude, so altitude means kind of distance above the surface of the Earth, so not from the center of the Earth. Okay, you have to add about 6,300 kilometers if you want to know the nominal I guess you could call it nominal radius of an orbital plane. Okay, so they're about 20,000 kilometers above the surface of the Earth. And why this is that equates to approximately a 12-hour period. Okay, what it actually is it's 12 sidereal hours, okay, which means that a satellite will reset itself. It'll be back in the exact same position relative to the Earth every 24 hours. Okay, we'll talk a little bit more about that coming up. GPS is designed for worldwide continuous coverage. Okay, so in theory, every square inch of the Earth, if you're obviously not in a cave or underground or something like that, right, provided you have a clear view of the sky, GPS should work. It works via, it's supposed to say line of sight. Okay, it works via line of sight in all weather conditions. Now we'll look a little bit about the weather conditions. That's largely what we would call the tropospheric effect for at least Earth-based weather. And as the troposphere changes, okay, as your height on the ground actually changes, okay, this is where we can start having substantial error, or for certain aspects, substantial error occur. Okay, so we'll talk more about how weather affects satellite positioning. Now again, maybe getting a little ahead of ourselves, but weather is actually broken into kind of two types. So our traditional definition of weather, which is Earth-based weather. We also have something that is coined space weather, okay, which is weather that doesn't affect us. You know, that it's, if there's space weather, it's not going to rain, okay, or something like that. So space weather, you know, explains or can be classified as like why we have the northern lights and things like that, those types of effects. Anyways, we'll talk more about the atmospheric errors and effects that can be an issue with GPS. So currently data is transmitted on 2 carrier ultra-high frequencies, or UHF frequencies. And we call these carriers the L1 carrier and respectively the L2 carrier. All right, there's a new carrier coming up that's going to be called the L5, and there are a handful of satellites that are currently in orbit. I'm not sure, might have to double check that. I'm getting confused right now as to what satellite classification supports L5, but I think they're the current a block of satellites that are being launched support the L5 frequency, though it hasn't reached full operational capacity, right? It's currently being tested and ensuring that everything's working properly. I will talk more about what's called the modernization of GPS, which is currently happening. As technology evolves, you know, transistors get smaller, and you know, everything like that, from software and hardware, the satellites are evolving as well. All right, so we're still not launching, you know, the same satellite that was launched in the 1980s today. Obviously, we're launching a much more sophisticated satellite today, and hence the whole system is being modernized. But in short, we're gonna limit our conversation, or the very specific details of our conversation, to the areas that are applicable for civilian use, because that's obviously important to us. So we have our carrier frequency. Okay, so we can just think of that as a sinusoidal wave. Okay, now there's 2 of these at different respective frequencies. Okay, let's just say that this is the L1 frequency. And then what we say is modulated, or basically kind of information is added to these carrier frequencies. Okay, so the carrier frequency itself is of no interest, at least in our discussion today. That's not exactly true. For some high precision applications, the carrier carrier frequency is very important. But we can think of that there's pieces of information, data, ones and zeros, right? Binary information that's added. So you can think of them as like little packets, okay, little boxes. And inside this little box, there is information that we would like, you know, a number, you know, the number 5, the number -109. Now there's different types of data that are modulated onto our carrier frequency. Now they're modulated or added to the carrier frequency because ultimately, so over here, let's say, is our satellite. So there's our satellite with its solar panels, and down here on the ground is our user receiver. So obviously we want this data to reach the end user, because the user needs that data, those numbers, in order to solve problems like where are they? What are my X, Y, and Z coordinates, for example, things like that. So what we're talking about here is There are different types of data that are modulated or added to the carrier frequency, that are then transmitted. So here's our transmit direction. So transmit from the satellite to the receiver. Okay, so some of the codes, we call these codes. Okay, like the pieces of data, we call them codes. Okay, they have specific structure and they mean certain things. The one that we're interested in is what's called the CA code, okay, which stands for course acquisition. A way that you can think of it is that it starts with the letter C, and the word civilian also starts with the letter C, so that's the code that we're primarily interested in. Okay, and we use codes, they're also called ranging codes, which is we can actually, so if this is a CA code, okay, piece of data, we can actually use this piece of data to determine the range or the distance between the satellite and the receiver. So let's just call that P for now. All right, so this is an a measurement that we need in order to determine where we are. Okay, ultimately we also need the coordinates of the satellite. So then it kind of gets closer just back to traditional surveying where we consider the satellite to be a control point with known coordinates. We then have a distance measurement to that control point, and we can use then several of these types of measurements to several satellites to basically figure out where we are. And we'll talk about this coming up, called the fundamental positioning problem. However, there are other codes that are modulated. One is the P code, okay, which is known as the precise code. The precise code is actually encrypted, okay, what's known as anti-spoofing, which is the P code is encrypted. Then you obviously need the decryption capabilities to utilize the P code. So for us directly, in the easiest sense, we're not interested in, or we don't utilize the P code as being civilians. All right, there are new codes being added. One example is something called the M code, which is a new military code, okay, which is ultimately going to be replacing, or it's designed to be a better version or perform, the same thing as the P code, but better. And there's also other civilian signals being added as well. Okay, so right now there's only a CA code on L1, and however, there's a new CA code that's being added to L2. And pretty soon, even our recreational grade, lowest grade receivers are going to be able to perform these types of measurements on both frequencies, L1 and L2. So currently, for the lowest grade, we can only make measurements on L1, or what we call single frequency receivers. There's a great benefit to being able to make these types of measurements on 2 or more frequencies. All right, and we'll talk more about that coming up as this course progresses along. So GPS is most broad scoped classified as containing 3 what are known as segments. The first segment we call the GPS control segment. Okay, and this is the network of infrastructure that exists to basically keep GPS afloat. Okay, float meaning, right, the proverbial just keeping the system working, okay, up in space. So it's military owned and operated. There is a master control station that's located at Shriver Air Force Base, previously known as Falcon Air Force Base in Colorado Springs. And now in the original design, there was Hawaii, Ascension Island, Diego Garcia, and Kwajalein were monitoring stations where they would have GPS receivers, slightly more sophisticated, okay, GPS receivers that would be tracking the information being sent out from each and every satellite. All right, so the control segment has lots and lots of responsibilities, but some important ones to understand are that they monitor the system to ensure, so I'm running out of screen space here, they monitor the system to ensure that the signals that are being sent out by the GPS satellites are what they are expected to be. Okay, there's obviously the possibility where, say, a bad upload or there's a bad piece of hardware in one of the satellites, and then the information that's being sent out to all the users worldwide is wrong. All right, and this can obviously cause some positional errors. And we have some cases, some known historical cases of this happening, and we'll look at those later on in this course to see how much, say, a single satellite, if it's sending out bad data, how that can affect positional solutions kind of worldwide. So in the original design, there was only the 5. So here's Shriver Air Force Base, Colorado, Hawaii. I believe this is Ascension Island, Diego Garcia, and Kwajalein, I believe. These are all islands where the U.S. has Air Force bases. Okay, now the distribution of these monitoring stations was designed so at any moment in time, the US government would have control over the satellites. So if they needed to send up a command saying, hey, you're not sending out the right data, or right, just to be able to communicate with the satellites, they could do so at any moment in time. Now this is being revamped with the modernization. They're adding more and more, like Cape Canaveral, I know now, somewhere down here in Florida. There's monitoring and transmission stations, and I think somewhere in Europe, and kind of scattered all over the place now. The monitoring stations are increasing all the time. Okay, so that's one important aspect, is that GPS, the control segment monitors the information coming from the satellites. However, so maybe this second one should have come first, but what they do is they also they provide the orbital information, okay, to the satellites. Now, what I mean by orbital information is, with these monitoring stations, they track the satellites, and what they do is, using some very sophisticated mathematics, they perform prediction modeling, and they predict. And these predictions are generally about 2 hours in time. So what they do is, so just kind of ignoring maybe we'll draw it over here. So if this is, let's say, the orbital path of a satellite, in order to utilize the satellite, if we go back a screen, you'll remember that we needed to know the X, Y, and Z position of the satellite in order to use it. It acts as a control point. Well, how do we get this information? Again, the system's very dynamic, right? 4-dimensional times the 4th dimension, where we'll talk about this, but the satellite moves at about 4 kilometers per second. So these coordinates then, from 1 second to the next, would be moving about 4 kilometers. So obviously, what I'm saying is that the X, Y, Z are changing very, very, very quickly. So what happens is that the control segment monitors, okay, they basically make measurements exactly where the satellite, was, okay, and they use this actual information then to predict. They basically continue, some type of analysis forward, and then they predict, okay, for these 2 hours, let's say that's 2 hours of time, this is going to be the actual or predicted orbit of the satellite. Okay, then for the next 2 hours, or then what they do is then they monitor the satellite during these 2 hours, right, and they use that, and then they come up with new estimates, and this process continues every second of every day, over and over and over again. So we have all of these generally 2 to 3 hour kind of prediction windows. All right, and the Department of Defense, or the control segment, is required, or one of their responsibilities is to provide this information. They upload it to the satellites, so they monitor it from the ground, and then they have communication, right? So this is like a satellite dish, right? Somewhere down here, they have these located. I think some of these are upload stations as well. And then so once the satellite is right in view, or right, they can upload a signal to the satellite, and they can send these blocks of information to the satellite. And then the satellite knows, okay, when I cross this threshold, the satellite switches from broadcasting this set of data to this set of data. Now, these sets of data we call ephemeris. Okay, for one, so just the orbital information is what we call ephemeris data, or ephemeris sets. There's also the satellites, as we'll learn, because it's 4-dimensional and time becomes very important. The satellite also broadcasts down information about its clock. Okay, these are basically flying atomic clocks, very, very accurate, stable clocks. Okay, we'll better understand the importance of the ability to determine very precise time with GPS later on. And then there's also, I'm just going to say, other data, okay, that they send down. We'll talk again more about this later on. So all 3 of these data sources, okay, again, get modulated into a data packet. So there's one of our little boxes. And again, they get added to the carrier frequencies, and they get sent down. All right, we call this kind of overall information, we call it the nav data, or navigation data. Okay, and it's broadcast in what's called the navigational message. So we call this here a data packet of the nav message. And we'll talk more about this coming up again. So again, I just wanted to give you some information about the roles and responsibilities of the GPS control segment. And it's really the easiest thing to think of it is it's monitor and prediction. Okay, without these two, really, without the monitoring is used in the prediction and things like that. But again, it's the easiest way to think of this is that we need to know exactly, or as best as possible. We'll talk about the accuracy of this information, but we need to know the XYZ position of the satellite at very specific moments in time. And this is all thanks to the control segment. The next segment is broken down into what hardware and software, I guess in theory, is up in space. So the GPS space segment contains the hardware that's up in space. So each satellite is made up of radio transceivers. So again, the word transceiver means it has the capability of transmitting, as well as it has the capability of ceiver, which means it has the capability of receiving information. Okay, so now again, just to demystify, we, the users of GPS, we do not transmit anything that the GPS satellites receive. We do not directly communicate with the GPS satellites. They communicate with us. It's a one-way communication. So again, here's a satellite, here's us, the receiver down on Earth, right? The communication is purely one way. It's this way. There is no communication this way from the civilian side, so civil side, up to the satellites. Obviously, the military, DoD, has the ability to upload, right? Communicate with its satellite, but we do not. Okay, sorry, I kind of, can I erase that? Sure, I can. Erase. Okay, as I mentioned, there are atomic clocks. The importance of this we'll talk more about. Okay, atomic clocks. There's a redundancy here. Okay, generally 2, 3, maybe some satellites at one point in time even had 4 clocks. Okay, so there's redundancy. Basically, when one clock fails, the other, another clock would be there with the ability to turn on. Excuse me. There's obviously computing systems, right? Systems that are going to receive the upload information, do some processing, take the information and send it back down. And again, the satellites are getting smarter and smarter as GPS is being modernized. They're the latest block of satellites. They're able to actually communicate between each other. All right, and they're actually able to range between each other as well, with the idea that if for some reason the Department of Defense, say that there was, a war or something like that, and the Department of Defense lost all of its capabilities of communicating with its GPS satellites, the network of satellites themselves, I'll draw in one more here, is able to range with respect to one another. And then in this case then, so the monitoring stations again would be down here on the ground, and we all know what their job is now. So this is, say, a monitoring station, right, which would be monitoring the signals and this and that. The network of satellites themselves are becoming smart enough to range between each other and then provide updates. Oh, you know what? This should be what your next 2 hours or more, of orbital information should be. This should be what your next 2 hours of orbital information should be. Okay, so it's this autonomous capabilities of the satellite network itself, okay, which obviously requires computers and things of that nature. There's power systems, as I think we all know. I always draw my little bow ties here with our solar panels out on the side, which is the primary recharging, right, or the sole recharging capabilities of the satellites. Okay, they run off of batteries that are recharged by the solar panels. Okay, at points in time, certainly the satellites will be shadowed with respect to the sun by the Earth. Okay, so the ability to have continuous power is obviously there for the electronics. And then there are propulsion systems. Now again, I think we talked about this possibly in Geodesy or something, but the satellites themselves do not have permanent rocket boosters on them that are constantly, here's my little flame, okay, that are constantly running in order to propel the satellite forward in its orbit. As soon as the satellite, it's when it's on the big rocket and it's launched and it reaches orbit, okay, in theory, it should stay there forever. Now, because of gravity effects and other forces and this and that, the satellite's orbit will change over time, right? It'll decay or it will increase depending on certain factors. However, though, another responsibility of the Department of Defense is because they monitor all the satellites. At times, they might say, "Oh, you know what? We want to do a repositioning maneuver, all right, and bump this satellite up a little bit or change its position, excuse me, slightly within its current orbit." So there are small little jet nozzles. I'm not an astronaut, obviously, so I don't know the technical terms for these things, but I always say, like, if you think of the movie Apollo 13, you know, when they're spinning their spacecraft around, there's little puffs of looks like air, you know, or gas that comes out. You can kind of think of those systems being on board the satellites, so they can make, you know, they can apply a little bit of force, so they puff out some gas this way, and the satellite's going to move in this direction. They puff out a little bit of gas that way, and the satellite's generally going to move in that direction, thanks to Newton and his laws. So anyway, so there are these propulsion systems that exist on the satellites. But again, there's no oxygen in space, so the oxygen needs to be oxygen needs to be included in the fuel. Okay, so there's only certain types of solid fuels, okay, or fuels that you need to pack onto the satellite before you launch it. And once those fuels run out, well, then obviously the ability to reposition the satellite goes away. Okay, so with that, also, you know, the ability for the atomic clocks to, you know, run forever and maintain accuracy, and the computers not to fail, and the power systems, you know, the batteries not to, you know, fail, things like that. Each satellite does have a life expectancy, so let's just call it LE for life expectancy, and it's a function of a lot of things, but each satellite was designed for so many years of service. Okay, and now those estimates, thankfully, have largely proven pessimistic from the manufacturers. Okay, so like Rockwell and Boeing and some of these other companies, right, that are contracted to build the satellites, you know, they come up with saying, yeah, this satellite is designed to last for 10 years. And there's been some satellites that have lasted for like over 3 times their life expectancy, okay, which is obviously a welcomed, from a financial point of view, it's welcomed. However, from a productivity point of view, maybe it's not so good, meaning that if that satellite failed when it was supposed to, you know, the requirement would exist for the satellite to be replaced. But again, that's a balancing act with regards to the financial side of launching satellites. Regardless, the first classification of GPS satellites that were launched were called Block 1 satellites, and this were largely considered the testing satellites. Okay, from 1978 to 1985. So real quick, none of these satellites still exist with regards to, you know, they're not operating. Okay, they were intended for research and development and had a 4.5 expected or life expectancy. No anti-spoofing capabilities, which means, again, we talked real quick about anti-spoofing, which just means the P code, okay, that precise code was encrypted, so encrypt, okay, to become what is generally called the Y code. Okay, so the P code plus encryption is what is generally referred to as the Y code. So these first satellites did nothing with regards to the encryption. So hence the P code was just the P code, and you could ultimately utilize the P code in your measurements. Okay, all Block 1 satellites have been deactivated. The second classification of GPS satellites, which were really the first round of production satellites, which is still actually, by the way, the current block, in the biggest sense, the current block of satellites that we're using, which are called the Block 2 satellites. Okay, so even the launch last month in March 2015 was still a Block 2 satellite. Okay, it was called a Block 2F satellite, which we'll talk about here coming up. Okay, so they're given specific space vehicle numbers, or we might call them SVNs. Generally, we'll use a different classification for satellites, which we'll call the satellites by their PRN, which stands for pseudo-random noise code. Okay, so there's very specific satellites. Pardon me, let me rephrase that. There's very specific, if we remember, we talked about the CA code. Okay, there's only a definitive set, which I think there's 32 usable, sorry, I'm running out of space here, usable CA codes. Okay, so what happens, so say in 1986, okay, so PRN code number 1 was assigned to satellite vehicle number whatever it was. Okay, so then let's say 15 years later, that satellite, let's say it was satellite 17, that satellite was decommissioned, okay, no longer was operational, and then a new satellite was launched. Let's say that that satellite was satellite 31, and then satellite 31 started using PRN code 1. Okay, so PRN codes will be utilized, and I believe there's only 1 to 32 for PRN numbers, versus satellite numbers are not reused. Okay, every satellite vehicle is given a new number. So there's different identifiers for how do we identify a specific satellite. Okay, so PRN codes are reusable numbers over time that can apply to different individual satellites, versus satellite numbers are a unique identifier for a specific satellite. The Block 2 satellites were designed to provide 14 days of operation without contact from CS, means the control segment. So this means that the network of satellites would be operational if the control segment was not able to communicate with them for a 14-day period. Basically, after that, the accuracy of the information coming from the satellites would just degrade and degrade and degrade. Okay, so it basically meant that they needed continuous communication, which is what's desired even today's current system. The satellites, the control segment wants to continuously communicate and be uploading, not constantly, but very, very frequently, new information to the satellites. Okay, all Block 2 by themselves, okay, without any additional classifiers after the Block 2, as we'll see coming up here, have been deactivated. Okay, so the third classifier was not Block 3. That's what we're progressing to here coming up in the hopefully not too distant future. But we're still in the Block 2 era, but now we have these additional identifiers. And the next additional identifier was this Block 2A satellite. And Block 2A satellites were launched between 1990 and 1997. Okay, so again, technology evolved since, say the early 90s to 1997. These were space vehicles 22 through 40. Okay, they were designed to provide 180 days of operation without contact from the control segment. So again, that autonomous ability for the satellite networks increased with regards to when the Block 2A satellites were introduced. Now this stat is a little bit older. Now I'm not sure as to what that is today. Might be 0, might be still a handful of these satellites are still active within the constellation. So if you're ever looking on your GPS receiver and you're able to look and see the SV numbers as an indicator, if you see an SV number in between 22 and 40, that gives you indication that that is a Block 2A satellite. The design life for the Block 2 and Block 2A satellites were 7.3 years. Okay, and each, so here you go, so it did contain 4 atomic clocks, 2 cesium-based atomic clocks and 2 rubidium-based atomic clocks, which again are just different elements, different means of keeping time using cesium atoms and rubidium atoms. Okay, and there's benefits and disadvantages, if you want to think of it that way, to each. They have what's called SA, which stands for selective availability. We'll talk about that coming up, as well as it did introduce the anti-spoofing capability. So that's where, again, P becomes encrypted to Y for anti-spoofing. Okay, and SA, or selective availability, as I mentioned, we'll talk about coming up. The fourth classification of satellites that were launched between 97 and 2004 were called Block 2R satellites. Okay, I think are replacement or replenishment. I forget what the R stands for, but something along those lines. There are space vehicle numbers 41 through 62. Okay, there you go, replenishment satellites. 14 days of operation, okay, without contact from CS, but 180 days of auto navigation. So again, the system, basically what this means is the system starts degrading after 14 days, but it can still be utilized. I'm sure there's probably published, accuracy levels for 180 days. And this is where I believe that self-ranging between satellites was introduced. Yes, satellites range and communicate with each other and estimate the updated ephemeris. So again, that's the orbital information. Okay, so the satellites themselves basically determine their best orbital parameters without contact from any of the monitoring stations or the network down on the ground. Okay, so again, as of 5 years ago, there's still 20 of these satellites in use. Sorry, this is a kind of precursor here. We're going to talk about the next classification, which was Block 2R, which we're currently talking about, but Block 2RM satellites. Okay, so we call this the 5th classification, and this is incorrect because these are no longer being launched. Okay, the ones that are being launched currently are Block 2F, okay, 2F satellites, which we'll talk about next. Okay, so I forget the range that they went up to. Maybe, so 1, 2, 3, 4, 5, 6, 7, 8. So maybe there was 10 to 12 of them launched, I'm going to estimate, before the Block 2Fs were beginning to be launched. Okay, so it stands for Modified Block 2R. And largely where this came about is technology was or had evolved. Okay, the U.S. government would send out contracts to Boeing or Lockheed Martin or something, saying, okay, we want you to create 20 of this, and they they give them the big stack of documents for the GPS satellite that they wanted them to create. But then again, because of the life expectancy of the individual satellites lasting longer, right? We're not going to take this satellite out of orbit if it's still working perfectly fine. Okay, so what they would do then is they basically, started to stockpile all these satellites. And then, they'd realize, 5 years had passed and technology had evolved, over that 5-year period. So it's like, okay, so now we need to launch a new satellite. So are we just going to launch something that was created, 5 maybe plus years ago? Or should we consider, making these satellites more up to date before we launch them? And that's largely what this modified Block 2R basically became. So they were originally designed as Block 2R satellites, okay, and then they were modified to include, better capabilities and this and that. Okay, so this is the first satellite that added that new military code that we talked about. So this is really kind of considered the first satellite that kind of began the modernization effort within GPS. Okay, as well as it added that CA code onto the L2 frequency. Okay, so we're getting very close to being L2. It's called L2C. That's the code. Okay, we just call CA code the CA code that's on L1. We call L2C the CA code that's on L2. Okay, and now why that is the CA code on L1 has a different structure than the CA code on L2. Okay, again, based on advancements. The CA code on L2 is a little bit more advanced. All right, and we'll get, again, a little bit more into that. Not too much. It's pretty complicated stuff, but... And these were designed for about 8 years, and they used 3 rubidium atomic clocks. And again, they support selective availability as well as anti-spoofing. Okay. And so satellites of the future. So this is actually kind of this 6th classification is satellites of the now, which is the Block 2F satellites. Okay, and this adds the M code and the CA code, so just like the Block 2R, but it also now starts using this L5 frequency. So this is where I wasn't quite sure, but yes, I was right that in the current GPS constellation, there are a handful of satellites that are broadcasting the L5 frequency and information on L5 as well. Okay. The 7th classification of satellites, if we continue this mantra down, is what we call the Block 3 satellites. So now it's this paradigm shift from Block 2 to Block 3. Okay, so it says here, according to this, scheduled launch of 2016. The earliest that I've most recently read is now 2016 or next year, where they might be launching a Block 3 satellite. I believe the first production Block 3 satellite is currently undergoing, the plethora of tests that the satellites go through to ensure that, they can survive launch and everything like that. So we'll see. We're getting very, very close to the realization of Block 3 satellites. Okay. Now the only thing with that, and we're going to jump off of the lecture here for a second and go to the civilian GPS website, is that in order to support this new advanced hardware in space, so if here's again space, so if we have advanced, let's just draw it, as a plus. If we have advanced hardware, advanced satellites that are up in space, obviously then on the ground, our monitoring network and things like that also need to be modernized or updated. And right now, this is kind of one of the current efforts, or let's call it difficulties, is ensuring that we have an infrastructure on the ground. So that, again, this is the Earth, an infrastructure on the ground for the control segment to support GPS Block 3. Okay, so we can't just launch these and start utilizing them. All right, I guess in theory maybe we could, but obviously we want to make sure again that we can monitor the information that's coming from them to ensure that they're meeting their objectives. So it's not just the satellites in space, and that's where again this discussion on the different segments of GPS are very important for a user to understand. So with that, if we jump off here and we go to the what I call our official U.S. government information about the global positioning system and related topics. www.gps.gov. And there's a whole bunch of information on here. What is GPS? How does it work? All this type of stuff. So I just wanted to watch this quick little video here on GPS modernization. there we go. So there's a, a pretty good overview, at least, as to what GPS is all about, and it starts talking or hitting on some topics about what we're going to discuss next, which is the user segment, which is the third and final segment of GPS. Having this wonderful system, but if no one utilized it, well, then obviously it wouldn't really be of any benefit. So first, before we leave the gps.gov site, there's a whole bunch of other information with regards to what's happening. So here under Systems, GPS Overview, the Space segment. So if we click on this, this should be talking about what's currently happening with regards to the satellites. Okay, so it talks a little bit about the information that we just discussed. Okay, and so here you go. Here's the information about what's currently in operation. So there's three Block 2A satellites that are operational, 12 Block 2R, 7 Block 2RM, and 9 Block 2F. And again, GPS 3 is the next. There probably will be a couple more Block 2F launches with regards to replenishing the satellites that are in orbit before they get to Block 3. Okay, so there's some information there. And then under control segment, this is where it should be talking about OCX, I believe is what it's called, which is the next, here we go, OCX, which is the next generation of operational control system. And this is, again, what the system that's basically needed in order to support the evolution of GPS and GPS 3. So I would encourage you, if you're interested, to watch this video in your own time. It's not very long, or read up about some of the information or the modernization that's happening within the control segment of GPS, because it's very important to understand that. Okay, so maybe I should have went one more slide in the video there. It talked about another additional signal called L1C. And now what L1C is, as I talked about, they call it, the international interoperability signal, which as we're going to conclude this lecture with, we'll talk quickly about the other. GPS, again, is just one flavoring of GNSS, Global Navigation Satellite System. So GPS is the US specific system, and again, there are other GNSSs, okay, which we'll talk about later on. So the design of this L1C, it's a civilian signal that's going to be on L1. And you might be saying, well, isn't there already a civilian signal CA code on L1? And yes, there is. Okay, but again, this is called L1C. And the idea is that eventually this will replace the existing CA code on L1. However, they will coexist for probably a significant period of time. One other thing is, back to my initial slide there, I said that the system costs $6 billion, while we just heard in the video that up until now, kind of the price tag has been about $35 billion with regards to the cost to create and support and modernize GPS to date. So again, L1C allows for greater civilian interoperability with Galileo's L1 signal, as well as some of the other, so we, again, don't want to talk too specific about those, but some of the other GNSSs. So the idea is eventually you might just have a single receiver that all it does is, say, track L1C and L2C. Okay, well, now L2C is specific to GPS, but let's just say it only tracks L1C. Well, then your receiver, it doesn't care that if it's tracking GPS or if it's tracking Galileo or if it's tracking some of these other GNSSs. It's just they're all going to be kind of part of one big system, if you want to think of it that way. And that's, again, one of the planned benefits for L1C. But as you might imagine, it requires a large degree of cooperation in order for everybody to agree to support this L1C. But at least in theory to date, that is the idea behind L1C. Okay, we'll skip over this video, and I think this link possibly doesn't work anymore, but you can just Google or go on YouTube and look for GPS satellite explosion. Actually, the very first time that the Block 2R satellite was attempted to be launched, it actually exploded shortly after takeoff. My understanding is correct, the launch vehicle was actually self-destructed because they realized that they had lost control of it. Okay, so some major malfunction. And anyways, it's an interesting video to watch. Okay, so the GPS constellation, as we quickly went over, there are 6 orbital planes okay, which means that they're 60 degrees apart. They're inclined with respect to the equator by 55 degrees. So if we draw the Earth, North Pole, South Pole down here, and here's the equatorial plane that would be coming out of the page at you. The GPS orbits, so I can only draw an orbit as kind of a diagonal line here, but imagine it as being a circle. Okay, it's very, very nearly circular. Okay, so this again, orbit would be going into the page, say up here, and then it'd be coming out of the page right here, and then it'd be following a circle. Okay, the inclination angle is this angle with respect to the equator, and it's about 55 degrees on average for GPS satellites. So it's designed for 24 satellites, so it means generally there's about 4 to 6 or more satellites per plane. So it means that there's basically, let's say 6 satellites that follow exactly the same orbit, okay, more or less. They basically kind of think of them as like a train. They just follow, one after the other. But obviously they're not connected to one another in the physical sense. So satellites locations optimized for coverage, some world areas emphasized. So the distribution as to where this satellite's going to be here and this satellite's going to be here, and you got another plane over here, right, and things like that. So the distribution of the satellites is a fairly complex problem, which we will not be looking at. There are some kind of classical models for how orbits and positions within orbits are determined for best coverage and things like that. But again, there is a rhyme or reason for why a satellite is positioned here within this plane or here within this plane and things like that. Okay. So I do have this physical model here that I don't know if it's linked into the document. I tried to link, this is an active PDF that I tried to link directly or embed, pardon me, into the PDF or into the PowerPoint here. Okay, let's see if it launches. Yes, it does. Okay, great. So if you're looking at this 3D person, okay. So yeah, so sometimes when PowerPoint updates or things like that, it doesn't necessarily like some of the previous embeddings. So I'll make sure that I put this document on the course website as well. And I cannot, just give me 1 minute to find that document. Okay, see if this one works a little better. All right, so if we click on it, it's a PDF, but PDFs can actually embed 3D models, which means you can then click on them and rotate them around and zoom in and zoom out. So with this, there's a whole bunch of lines and stuff, but the 6 orbital planes are shown each as a different color. Okay, so if I try to rotate this around, so right now it's kind of like the sketch that I drew. So North Pole up here, South Pole down here, and the equatorial plane, as you can see, is coming out towards you. And then if we look at any one of these individuals, so again, I'm colorblind, but I think you can differentiate that there's 6 different colors here. So if we look at any one of these, so I can tell that that's white, so I'm going to orientate the white kind of just like how I added in the figure. So here's the white orbit, and again, it's actually circular, as you can see, okay, or nearly circular. It's actually elliptic, but it's very nearly circular. Okay, and then again, this angle between the orbit and the equatorial plane is 55 degrees. So that's what we call the inclination angle. So then if we take this pierce point, okay, so where this orbit is piercing the equatorial plane, and we were to draw a line from that pierce point to the center of the Earth, and that's what this line shows. Okay, and we do that for each respective orbit. Okay, so here I'm going to make the assumption that this is blue. Okay, so if we go from the blue and intersect the Earth, the angle between those two lines is the 60 degrees as we see here. Okay, so that's the distribution of the orbits. They're spaced 6 orbits and 360 degrees means that they're 60 degrees apart. Okay, so if we orbit this around, you can see that each of these orbits is exactly 55 degrees. Okay, well, not exactly, it's designed to be 55 degrees, but there are 6 of them before they repeat. Okay, and you can see then that the orbits that are spaced 180 degrees apart, like the red and the white orbit in this case, would in theory share these intersection points. Now these intersection points have specific names. They're called the ascending node and the descending node of the orbit. Okay, but again, they're not actually the same point in space, so there's no risk of the red satellite crashing into the white satellite. Again, that's all planned in the spacing of satellites and things like that. But again, in theory, they would share an ascending and descending node. However, they would be different, which meaning, so let's just say that all the satellites are orbiting in a, I guess, kind of counterclockwise orientation, which means that in this case, this satellite here would be rising, so it would be traveling in this fashion. However, this red satellite would be traveling in this fashion. So in this case, this node would be the ascending node, which is the southern hemisphere to northern hemisphere node for the white satellite, but it would be the descending node for the red satellite, which means it's the north to south node for the red satellite. Okay, just some jargon there with regards to these specific points. Okay, so that is a better, it's a 3D active model to try to illustrate the orbits of the satellites. Okay, and again, you can see here that the satellites are not designed to directly cross over the north as well as the south poles. Okay, so if you're standing on the north and south poles, you'd never see a satellite travel directly above you. Okay, in theory, how this works, there's actually a correlation with the inclination angle, okay, and the maximum latitude that you could be standing and have a satellite go directly overhead. And I'll let you try to look at the geometry and figure that out. Okay, so anyway, so more on the distribution of the satellites here coming up. Okay, and one of our projects and things like that, we'll be looking at some of these effects. Okay, so again, please feel free to view this model, right, to get a better understanding as to how the GPS satellites are actually distributed. There's one other, I just want to browse to this site. It's on GPS World, and I was meaning to bring this up. If you Google GPS Easy Suite, why I'm going to bring this up, and then you go to, or not GPS World, Inside GNSS, which is a publication. There's this nice little, it's an animated GIF, okay, or animated image, okay, this one right here. I really like this little image. I think it shows some really neat things. Okay, I'm just going to zoom in a little bit here on my webpage on the webpage here to show you. So the little dots here represent the satellites, okay, that they're orbiting within their planes. Now I think this is maybe 24 if anyone wants to pause it and count the individual dots. But they've done a lot of work in this little animated GIF in that the colors of the satellites change when they're utilized at this point. So this little blue point here on the Earth, okay, is where, let's say, a receiver is. And then you can see that the yellow or green lines will connect to the satellites, which means that currently this satellite is viewable or observable from the blue location. And when the line goes away, then the satellite becomes red, I think. Okay, so I'm just going to track this satellite here with my mouse so we can see it moving around. And then at some point in time, it becomes viewable by the blue. So there. Okay, I think I lost it, and maybe that was short. But anyways, it also shows the dynamics of the Earth's rotation with respect to the satellite orbits. Okay, so you can imagine that the white background here is space, and it's just fixed. Okay, the satellites just continue orbiting in a fixed orbit. You can think of it as a fixed orbit just over and over and over again. Okay, during that time period, the Earth is obviously rotating with respect to the fixed space. Okay, so if we were to track this, if we can watch this, so let me see. I'm going to look at this satellite here that I'm currently tracking. Okay, this one right here. And when it gets to the bottom here is when we're going to start. Okay, so we're going to watch. Okay, so right now. So what I want to see, okay, is actually, sorry, I've got to do this again. So next time it comes around, what I want to notice is so when this satellite's at the bottom, where is the blue dot? Okay, so right now the blue dot is pretty much right in line with kind of the orbit, if you will. Okay, so let's just watch. Hopefully everybody's watching that satellite come around. Okay, so it's going around. So that satellite now has made one rotation, one orbit. Okay, notice now the blue dot. Okay, it's now exactly opposite where it was when it started. Okay, let's keep watching that satellite. It's coming around. It's now at the top. Okay, coming back down. and right about now, so it's gone around twice, and what we notice though is that the blue dot is back to where it was. And that all has to do with that 12 sidereal hours. It means that each GPS satellite will make 2 complete orbits, okay, in 12 sidereal hours, or 1 complete rotation of the Earth. Okay, and that is a function of the distance, that 20,200 kilometers. That's really why the satellites were chosen at that altitude, to achieve that repeatability, okay, or 2 orbits in 24 sidereal hours. Other satellites, or other global navigation satellite systems are higher and lower respectively than the GPS orbits, okay, which means that they're going to have different repeatability times as to how many orbits are they going to do, before the system resets itself. System resetting itself meaning that the blue dot gets back to where it was and all the satellites are exactly where they were again. Okay, so anyways, this is a really nice little animated GIF that actually shows some really interesting dynamic properties of the satellites. Okay, and as you notice here, you can see that it's quoting the visible, how many satellites are visible. Okay, so if we try to find the minimum, it's probably for that, again, it's latitude, it's a function of latitude. So where is this latitude located on the Earth? Okay, so looking at, I think I saw for a second there, it dropped down to 6. Okay, 6 again. So again, if we watch this for 1 complete rotation of the Earth, we could find the minimum. But I believe it to be about 6 for kind of most of the populated world. Okay, so continuing on. So this is from 2010, so it's a little bit dated, obviously, but it tells us the information about the actual satellites. Okay, so here again we have the PRN numbers, which you can see go from 1 to 32. Okay, then there's also slot numbers, and then they specify what type of clock is being used and things like that. Okay, so there's lots of information that you can gain about the specifics of each individual satellite. Okay, so you could browse to that website to get a more modern snapshot of this information. Okay. So now finally into the last segment, our final segment, defining the biggest macroscopic picture of GPS, which is the user segment. And the video does a really good job of highlighting, a lot of user segments of GPS, or who uses GPS and for what, purposes. Okay, so real quick, we'll talk about the military. I think it's a little bit straightforward, and obviously with regards to the requirement to position troops, land, sea, and air, submarines, fighter planes, ground troops, tanks, all that type of stuff. All right, the real big test was the Gulf War, the first Gulf War, okay, which was in and around, I believe, 92, 93, something like that, if somebody wants to Google when the first Gulf War was, which was really the first big test for GPS, okay, from a military point of view. Hopefully we'd all understand that because of this line of sight requirement, which means if I'm a user on the ground and here I am with my GPS receiver, okay, and I need a clear view up to the sky in order to find my satellites and make measurements. Obviously, if I'm inside of a bunker or underground even, okay, so say I'm underground, and now I have my GPS receiver. Well, obviously my GPS receiver down here is just going to have a big fat question mark saying, well, I have no idea where you are. So it's not a perfect system from a military point of view with regards to the requirement for this line of sight up to the satellites. All right. However, there is research, augmentation systems, which means GPS plus some other sensors, okay, can produce, pretty good information as to where you are, say underground, or if you're, under a lot of trees or something like that. Okay. So for us though, we want to concentrate on the civilian side of GPS. That's obviously where we fall in, and the areas or applications of GPS that we are interested in. So the primary focus is on navigation. Okay, however, surveying industry has started to leverage GPS, and we're going to look at the high accuracy, high precision applications of GPS, like for surveying. Right, we're going to understand how does RTK work. Pardon me. How does RTK work? Cheap cost of GPS receivers is causing a rapid growth in civilian GPS applications. As I believe we're aware, I think every smartphone, produced in the last, let's safely say 5 years, I think it's even, longer than that, will have a GPS receiver built into it. All right. The ability to produce smaller and smaller, more miniature electronics, right, has why our cell phones keep getting thinner and thinner and things like that, but the technology keeps getting basically more powerful and powerful, all factors into this ability. Okay, so nowadays, as the video said, there are billions of users of GPS. Okay, so again, the video does a great job of discussing the user segments. We're going to concentrate on, eventually concentrate on, the positional side of stuff. So we're going to basically be concentrating more on kind of this type of applications for us here in our Geomatics program. All right, but however, right, military, or pardon me, emergency services, okay, emergency services utilize GPS. Okay, aviation utilizes GPS with the L5 as well. They want to be replacing some of the ground-based, radar-based systems with just using GPS. Okay, but obviously the system needs to be able to produce, very accurate, very reliable position estimates if we're going to start landing all airplanes, worldwide using GPS. This is kind of more, I guess this one and this one kind of are along the same. Let's just call it recreation. Okay, you want to, sail around the world. Well, you're probably going to want to have a GPS receiver if you want to do that. You want to, ski to the North Pole, right? Well, you're probably going to have a GPS receiver to do that. And then again, another interesting one for us around here is the precision ag. Okay, the ability to produce, better utilize, overlaps with combining and seeding especially, and spraying fertilizers and pesticides and things of that nature. Okay, so from an efficiency point of view, from a production point of view, precision ag is becoming big. Another one is machine control, which is kind of along the same lines. Okay, which is you take a bulldozer or a grader. Let me just kind of draw a crude bulldozer here. So here's our bulldozer with the blade and its tracks. And we want, we're creating a road. Okay, and we want this to be, exactly at a specific elevation. Well, let's just slap on some GPS on this bulldozer, and it'll ensure that, pretty much within a single pass, it'll be able to, follow exactly the elevation line that we want it to. So things of that, and that's generalized as machine control. Okay, which is again very similar to the concept of precision ag, but machine control concentrates a lot more on the vertical aspects as opposed to precision ag, which is largely more interested in the horizontal aspects of precise navigation. So as we talked about, when full operational capacity was reached, the Department of Defense guaranteed specific levels of accuracy. Okay, and currently for us, the civilians, we follow or utilize what's called the standard positioning service, which basically means that you're positioning using the CA code. So like your cell phone, okay, this is not talking about some of the trickery that we're going to look at with how can we get, like 1 centimeter positions with RTK. Okay, that's not this. So this is just like how accurate, guaranteed accuracy does your cell phone have, or something like that. And the current standard positioning service states that at a 95% confidence level, so 95% of the time, you're guaranteed to have a horizontal positional accuracy of 22.5 meters. There's lots of research done on this number, and it's realized that, over the last, I'd say 5 years, this number is realistically closer to about 7 meters. Okay, and I can produce some publications that state that. Okay, so it's, 22 is pretty pessimistic. Okay, it's more realistic about 7 meters, 95, or even greater than 95% of the time, pretty much worldwide. So it's very, very good if you think about it, right? You can buy a very inexpensive sensor, which is our GPS receiver, and you can position yourself anywhere on the globe with an accuracy of about 7 meters. That's pretty good. That's an amazing service. It'd be one thing if that service just existed, say, over the United States, but this is a global system. So I just still find it fascinating. Again, we haven't talked about SA. We've defined it as selective availability. Really quick, selective availability was an intentionally introduced error, okay, which was designed to degrade. Okay, going to draw a big minus there, to degrade the accuracy of GPS. Okay, unless you were an authorized user like the military. Okay, and with selective availability on, this number jumped up to 75 meters. Okay, which is obviously significantly worse. Pleased to say that since 2000, selective availability is turned off. We'll talk more thorough about selective availability in our errors coming up, but just at least for right now, an understanding as to what selective availability was, as in a past tense, because it's no longer applied, and it's extremely unlikely, basically impractical. I'm not even sure if the satellites that are being launched still support selective availability as a feature. I want to say that I've read something that says that they're not, so that it can't even really be turned back on because the hardware doesn't exist to support the system, which is a great thing. Okay, so some of the legacy users, you might be talking, your uncle or somebody, and might say, oh, GPS isn't that good. There's this error that's the government doesn't want it to be that good, and at one point in time that was true, and that was selective availability, but it's no longer the case. Okay, GPS is actually the same accuracy, more or less, for the military as it is for the civilians. Okay, now there's other benefits to the military, but from a meters north, south, east, west point of view, it's pretty much the same for civilians as it is military. Okay, so with this, we're going to jump into now a little bit more. It's still pretty broad strokes view of how GPS works. We now want to look at what I call the fundamental positioning concept. So how does GPS work from a positional sense? Okay, so again, here I am on the Earth with my receiver. How can I make these measurements to a set of satellites? Okay, so how can I make measurements to a set of satellites and figure out where I am? So again, the figuring out where I am, I'm always just going to say X, Y, Z. So I want to solve where am I, X, Y, Z on the Earth. So how does GPS allow us to solve this problem? And this is what I call the fundamental positioning concepts. So real quick, the answer is actually trilateration in space. Okay, trilateration we talked about when we talked about datum creation in geodesy. Trilateration means distance. Okay, triangulation means angles. So in this case, we use only distances to determine a position. Okay, so the distances in this case are these, what we call our ranges, the distance between our receiver and the respective satellites. And there's different symbols we're going to use, but the first one we're going to introduce is what we're going to call P. Okay, it stands for pseudo range. We'll talk about that coming up. So in this little example, we'd have P1, P2, and P3. Okay, which are distance measurements, no angles. There's no angle with respect to these, or azimuths or anything like that. It's just purely distances, and we want to use those distances to solve where we are. And the mathematics works out to, this is just purely a resectional problem. So in a horizontal sense, I could draw a little, maybe up here, I could draw a little map. Okay, and if I said that, okay, here's our total station now plunked down in the middle of a field, and I have a control point here, and a control point there, and a control point there, can I make a distance measurement, and distance measurement, and then figure out where my total station is? And we call this a resection problem in traditional surveying. It's the same exact concept. Okay, there's some differences, like our control points are moving because they're satellites and things like that, but the mathematics is still ultimately the same. Okay, so it's a complex problem because control points, the satellites, are not in a fixed position like they are in our traditional terrestrial sense, where we just have control points that are fixed on the ground. Okay, our control points are the satellites, and they're moving at about 4 kilometers a second, which means that obviously we now need time. Okay, time is irrelevant. T is X in this one. We don't care if we make this measurement now, or we make it tomorrow, or we made it yesterday. Okay, it's basically going to be the same. However, that does not hold in the case of GPS. So it's now time dependent. So T check mark. So it's 4-dimensional. So the 4 unknowns are X, Y, Z. Okay, more politically, as we learned about in geodesy, we know that we can take our curve to cart and cart to curve problems. Okay, so cart to curve is a problem that we're going to look at, which fundamentally GPS produces actually X, Y, Z coordinates in the WGS84 datum. Okay, and then if we want to know latitude, longitude, so phi, lambda, and lowercase h, we can take the Cartesian coordinates x, y, z and transform them, or convert them into phi, lambda, h. We looked at that in geodesy. Okay, so from a layman's point of view, latitude, longitude, and height makes a little bit more sense than this x, y, z, global Cartesian system. But nonetheless, this is the system. These are the coordinates that we fundamentally or intrinsically are going to be using. As well as there's this, it's a time unknown, which is called the receiver clock offset, and we'll explain a little bit more as to what that actually means. Okay, coming up here in a little bit. But it's basically, you can consider it as X, Y, Z, and T. Okay, those are the 4 unknowns. X, Y, Z, and time is really what we're trying to determine with GPS. So if we have 4 unknowns, we're going to need at least 4 observations or 4 equations in order to solve this problem. Now you've all taken an Intro to Least Squares course. Each one of these pseudo-ranges, we create an observation equation for the pseudo-range. Okay, so we're going to say P1 is equal to, and then there's a whole bunch of math. There's a square root and some, Pythagorean type stuff, right? X1 minus the x of the satellite squared plus y 1 minus y of the satellite squared, I guess it would be brackets here, squared, right, et cetera, et cetera, et cetera. So we have an observation equation. Well, if we have 4 unknowns, we're going to need 4 of these observation equations, or 4 pseudo-ranges, 4 pseudo-range measurements, okay, to 4 different satellites. Okay, the measurements need to be made at a constant moment in time, which means you can't make one observation to satellite 1 at time 1, and then another observation to satellite 1 at time 2, and another observation to satellite 1 at time 3. We can't use that, right? In order to solve this problem, we basically need to freeze frame everything. And we freeze frame everything by considering time to be constant for that one specific problem. Okay, so we need 4 different satellites that we need to make distance measurements to, or range measurements to, in order to solve for the unknowns. Okay, so simply put, the positional problem, right, relates to, well, if we look at it in a terrestrial sense, if I say that I am 67 kilometers from Regina, okay, so that's one distance measurement. Well, that allows me to safely say then that I'm then anywhere on this circle, because anywhere on that circle, the distance from the circle to Regina would be 67 kilometers. So we haven't figured out where we are, but we've at least narrowed our search down. Okay, we add another distance measurement. We now also add that we are 206 kilometers from Saskatoon. Well, now obviously our possibilities have narrowed down. You can probably see the answer to this problem, but we can either be here at the intersection of the 2 circles, or we can be here at the intersection of the 2 circles. So you can see by only making distance observations, we can start determining a position. And now finally, in this case, we add a third observation, which is I'm 161 kilometers from Swift Current. And now in this case, there's only one location where those 3 distance observations intersect. And in this case, the answer would be, well, I need to be somewhere in Moose Jaw then, if those are the 3 distance measurements that I'm making. Okay, so that's the concept of trilateration, or the concept of resecting via distances. All right, and that's the same thing, but now again, we just imagine that this is satellite number 1, and this is satellite number 2, and this is satellite number 3. All right, now these satellites are moving, so this has an orbit that way, this has an orbit that way, let's say, and this has an orbit this way, let's say. Now, in order to freeze frame everything, we need to freeze time. So you say, okay, at this moment in time, where were the satellites? What were the ranges from the satellites to my receiver? So this would be my receiver now, RX, my receiver. All right, and it's the same problem. We use distances alone to figure out where is our receiver on the globe. So how can we measure then? So we now understand the biggest picture of that. Well, let's look at the next problem, which is how can we determine, or how can we make this range measurement? Okay, as we showed before. If you remember, the communication between a satellite and our receiver down on the Earth is one way. Okay, that's the only way that information flows. Information does not flow back this way. Okay, so unlike, say, an EDM, where again an EDM pulses information, so it sends out information, it's reflected, and then it comes back. Okay, which means it's a two-way communication. So it's not the same. It's like your car radio. That's the analogy that I want you to understand. Okay, so it's really like the satellites are like a radio station. We tune to a specific frequency. Okay, so we have frequency. So let's say right 103.9 megahertz here in Moose Jaw. Okay, and then we start receiving those little data packets. And in the radio case, the little data packets would be the music. Okay, we start hearing the individual music notes, okay, that are coming down. Now in GPS, well, it's very similar. We have a satellite that acts as like the radio station. It's broadcasting on a specific frequency. So for us, 1575.42 is L1, okay, megahertz. And again, there's packets coming down. Okay, now in this case, the packets, well, they're used in a couple senses. Okay, one is the codes, the CA code. Okay, and we can actually use the information. So this is a CA code packet. We can use this piece of information to actually determine what that range is, the distance between our receiver and the satellite. Okay, In theory, you could actually do something very similar to this using, song information, okay, or a song. Okay, you'd need some other supporting systems to do it, but in theory you could. Okay, so how does that work? We haven't explained that yet. So the hint that I give you is, well, if I say that you're traveling in a car at 100 kilometers an hour, what do you need to know if I ask you how far have you gone? Okay, you're in a car. Your car is traveling 100 kilometers an hour. What else do you need to know in order to determine how far you've gone? Now, I think everybody's, capable, smart people, and you're all going to say, well, I would need to know time. The simple equation that distance is equal to velocity times time. So we're traveling at 100 kilometers per hour. That's our velocity or speed. And we travel that for 2 hours. So the hours would cancel. And then we could safely say that we've traveled 200 kilometers. We get a distance from that. Well, it's actually the same thing that we do here with regards to the CA code. Okay, what we actually measure, what our receiver actually measures is time. Okay, it measures basically how long did it take this CA packet of data to go from the satellite to our receiver on the ground. Okay, if it can measure time, it knows that that signal was traveling at a specific speed. Okay, well, in this case, it's electromagnetic energy, so it's traveling at the speed of light, c. So then we can simply get our range, so we can then simply say that P, our range measurement, okay, or more politically correct, our pseudo-range measurement, is equal to the c times, we don't actually call this t, we call it delta t, okay, which stands for what we call the transit time, okay, and that's how we can determine this range, by fundamentally measuring the transit time, how long it took this CA code packet to get from the satellite to the receiver. Well, now that's not straightforward how that happens, okay, but we'll talk about that next, but this is a fundamental concept to understand. So in the case of GPS, what is traveling actually from the satellite to us here on Earth? Well, we've been talking about it, it's the CA code, okay? The CA codes on satellites on the L1. Well, if we talk about the CA code, at least for right now, let's just limit our discussion that the CA code is only on L1. Okay, very soon there'll be a different version of CA also on L2 called L2C, which will make our lives a lot better because the errors that we can start removing if we have measurements on more than one frequency. Okay, but again, since, well, it's kind of my joke again, but since we're not traveling on the signals, it's not like we're in our car and we can look down and see that we're traveling that fast. How fast do we know, or how can we determine how fast a signal is traveling? Well, again, thanks to Einstein and physics and things like that, we know that electromagnetic energy, and that's all that the CA code really is, right? It's modulated electromagnetic, or information that's modulated on an electromagnetic signal. Okay, on a frequency, and we know that those signals travel at least in space, in vacuum, they travel at a constant velocity, which is the speed of light. Okay, 299,792,458 meters per second, or moving the decimal place 3 forward, we would say that that's that many kilometers per second, or very fast. So if we're able to measure the time it took the signal to travel, okay, so the signal is actually what we're looking at here is the CA code. Okay, if we can figure out how long it took a specific CA code to travel from the satellite to the receiver, we know that it's traveling at a certain speed, the speed of light, and hence we can determine distance. Okay, so now the bigger question. Okay, I understand that, but how can we determine, or how can we measure that time? Again, we call that time, we symbolize it as delta t, and we call it the transit. Okay, not transmit time. We're going to introduce something called the transmit time, which refers to a single point in time. The transit time is actually a difference between, okay, when it left and when it was received. Okay, it's a time duration. Okay, and we call it the transit time. In short, okay, without getting too detailed, we're going to relook at this when we expand our knowledge base. But the easiest way you can think of it is that the CA codes are time tagged, which means that when they leave the satellite, so just before, so I always draw this little humorous picture, just imagine that there's a line of CA codes. Okay, it's like a production line. There's all these little CA codes that are getting ready to be sent. Okay, they're on like a little conveyor belt or something. And here's the launch gate, okay, as to when they're going to be, shot off really fast at the speed of light from the satellite. Okay, well, what happens is just before this packet gets sent, you can think of it as it gets time stamped. Okay, you left at time t is equal to 2. Okay, off it goes. The next one comes up. Okay, you left exactly at time t is equal to 2.5. Off it goes, and you get the idea. So each one of these each one of these CA code packets is, you can think of it as that it's carrying along with it as it's traveling. Again, it's traveling down the CA code, so it's down the frequency roller coaster, I call it. Okay, so as it's being traveled at the speed of light, so it's going real fast to our receiver. Okay, it's carrying along with it. So let's say this one left at time t is equal to 1.5. Okay, so that goes down. So then what happens is, at our receiver side, our receiver receives the packet, it opens the box, and now this is the data packet opened, and it pulls out the piece of information that says, oh, you left at time t is equal to 1.5. Okay, and this is where the concept of clocks comes in. Obviously, the satellite needs to have a clock in order to basically, be performing these timestamps as these packets are being sent. And also, our receiver needs to have a clock inside of it as well. Okay. So let's just make the assumption that right now that the clock in our receiver and the clock in our satellite are exactly synchronized. So when this, increases by 1, this one exactly increases by 1. Okay, now when I say exactly, we're talking on the order of nanosecond. A nanosecond is 1 times 10 to the negative 9 seconds, or 0.1234567 8 zeros followed by a 1. That is the level of precision seconds. That's the level of precision that we're talking about. Okay, so when we measure the transit time, we actually want to be determining the transit time to the nanosecond level. And again, why that is remember, this number is so big that even if we make a small mismeasurement in the transit time, that's going to equate to our range, right? Remember, P is equal to C times delta T. So if we have, say, a 1 microsecond, which is times 10 to the 6 error in T, this is approximately 3 times 10 to the 8. Okay, if somebody multiplies those together, you're going to get a big error in range, like on the order of kilometers in range. Okay, so we need to be able to measure time very, very, very accurately and precisely, I should say. Okay, so we're assuming that our clocks are synchronized. So we know that this packet left the satellite at time t is equal to 1.5. Okay, let's just say it's received at the receiver exactly at time t is equal to 1.6. Okay, the receiver knows exactly when it was received. Well, then simply by differencing these numbers, the receive time, okay, versus, or pardon me, the receive time versus the what we call the transmit time when this signal left. If we difference those, right, we could get that, well, delta t would be equal to 0.1. This is figurative, okay? Well, we multiply that by the speed of light, and then we can figure out, well, then that must mean that this satellite is so many meters away from our receiver, and hence we can gain our range measurement. And that's how, using the code information, okay, the CA code, the P code actually works basically the same, okay? And that's how we use codes to determine range in a nutshell. Okay, so that's basically my demonstration. I'd stand up in class and have us throw a ball back and forth and have some, some phones that with their clocks to, measure when it left and when it was received, and we could figure out distance. But in essence, that's how it works. Okay, so this is just kind of the English for what I just went over, that when the signal leaves, it's stamped with the time that it left. When it's received, okay, is we basically look at the stamp time, compare it with the time that it was received to solve for the transit time. Times that by the speed of light, and we get our range. So then my question is, well, what assumption did we have to make? Well, we made the assumption that the clocks were exactly synchronized. Okay. Now, how can that happen? That's our next problem. Well, how can we exactly synchronize our receiver's clock with the satellite clock? Remember, a satellite's clock is an atomic clock, and it generally, it drifts very, very, very little. Okay. However, I'll tell you right now, the types of clocks that are used in our receivers are about the same accuracy as our wristwatch. Okay, it could be a quartz oscillator, a very inexpensive clock. Okay, and I think we've all done the experiment, or at least I hope we all have, where we've synchronized two watches together and we realize that it doesn't take very long. When they were both counting second by second, now a few minutes later, it's plain to see that they're no longer synchronized. One counts to 5 while the next one counts to 4, counts to 6, counts to 5. You get the idea. Okay, which means that there's no possible way, even if at one point in time we could synchronize our receiver's clock, our inexpensive receiver clock, with the satellite clock very quickly, that synchronization is going to degrade. And again, remember the level of synchronization we're looking for. We're looking for the nanosecond level of synchronization. So what happens is this introduces the fourth unknown within the problem. Okay, and we call this fourth unknown the receiver clock offset, okay, D capital T, which really all that means is our receiver's clock is going to be counting some time. Okay, it's going to be counting 1, 2, 3, when the satellite's clock could be counting, 1,000, 1,001, 1,002. Okay, they're going to be completely different time systems, not related to one another at all. Okay, but we make the assumption that at the exact moment when we make measurements, there is a very, very unique and distinct receiver clock offset. Okay, there's an offset that if we applied to our receiver's clock, that would exactly synchronize us with the satellite clock. Okay, and for right now, we're going to make the assumption that all satellites, okay, because they're atomic clocks, keep exactly the same time. Okay, we'll learn coming up that even the little teeny tiny bit of drift that occurs between, say on the, 1 times 10 to the negative 7, we still need to factor that in, okay, in order for our range measurements to work out. We'll talk more about that. But at least for right now, just assume that all satellites' clocks are exactly synchronized because they're atomic clocks. So this fourth unknown is what we call D big T. And it says at the exact moment of observation, what correction or offset would need to be applied to our receiver clock to exactly synchronize it with what we call GPS time, okay, or the time kept in the satellites in a loose sense. All right, so hence, if we add another unknown, right, we need to add another observation. So instead of just observing to 1, 2, and 3 satellites, we now need to observe to a fourth satellite in order to solve for the 4 unknowns, which is X, Y, and Z of our receiver. So where is our receiver? As well as at that moment in time, what is the receiver clock offset? Okay, and receiver clock offset, it's time dependent, which means when did you make the measurements? Did you make them now or did you make them now? The receiver clock offset at each one of those moments is going to be different, okay, at the nanosecond level. So receiver clock offset is not a constant, even if the receiver is sitting there stationary, okay? You can think of it as basically it's the drift. It's accounting for the drift of the receiver clock with respect to atomic clocks. So if we kind of spin this on its head, as the video discussed, even using a cheap, inexpensive receiver or clock, okay, the time that's kept in our receiver, okay, if we take our cheap time, let's call it our cheap time, the time that's kept in the clock itself of the receiver, if we apply this offset, now the accuracy and precision of this time now gets basically on the order of the nanosecond. Okay, it's usually a handful of nanoseconds, but it means that, my wristwatch, if it has a GPS receiver in it, okay, if the GPS receiver can actually set the time in my wristwatch can actually have the accuracy of an atomic clock. Okay, but it doesn't cost, and it's not nearly the size and complexity of an atomic clock. Okay, and this is where the video talked about financial institutions, where there's trillions of dollars in transactions, right? And money doesn't actually, I think we all know, right, how many people pay their bills by actually going out, going to the cash machine and taking out cash, then walking it over to the, SaskTel or something and then paying it. Well, maybe some of you still do. There's nothing wrong with that, but most of us, right, money is really just digital now. It's just a combination of ones and zeros. This is just binary information. Okay. What I'm saying is it's very important to keep track of exactly when these transactions are taking place. So time is very important from a financial point of view, okay, for interest rates, for a whole bunch of reasons, okay? So the financial institution or financial world, let's say, and the supporting, computer infrastructure and things like that are going to have time systems in place that actually have networks of GPS receivers. So there can be a GPS receiver here in Canada and a GPS receiver in, the South Africa, okay? And they can actually be synchronized exactly together. Okay, so say I want to, buy stock, and well, when exactly did I, say click the button to buy this stock? So here's the stock, and say there's a person in South Africa and there's a person in Canada. Okay, and we both want to buy this stock. Okay, well, basically, who did it first? Let's just say that ever got called into question. All right, well, if we have a very accurate time system that supports and it basically timestamps, well, no, he clicked this exactly at this time, time t is equal to 1.000000006. And he clicked it exactly at 1.000000008. Well, you can, if that ever got called into question, you can safely say that, well, I bought the stock first. Okay, for again, a very kind of out there example, but showing the importance of time systems and how GPS is utilized to create these accurate time systems. Okay, so now great, we've calculated the distances. So we now understand that we have satellites and we have a receiver, and we now understand how we can measure these distances. So let's call that P1 and let's call that P2. What else do we need to know though? Okay, so it's not only the distances. So again, we want to know X, Y, Z of our receiver. Okay, so the distances are one thing that we need. What else do we need to know? Well, in our example, what else did we have? Well, we had the positions of the cities, okay, which were our control points. So in this case, in order for these range measurements to be at all meaningful, we need to know, well, where was the control point at that moment in time, or i.e., what are the X, Y, Z coordinates of satellite, let's call this satellite 2 and satellite 1. Again, remember, we freeze frame everything at a specific moment in time. We make these observations now. Okay, where exactly was satellite 2? Where exactly was satellite 1? So in order to do this, okay, so again, satellite's position is not constant. It's moving about 4 kilometers a second based on their altitude. Okay, so it can only be considered constant with respect to time. Okay, so how then do we determine the satellite's positions? How do I gain information about, well, X, Y, Z and X, Y, Z? And again, we talked about this when we talked about the control segment, right? That one of their responsibilities was, well, okay, they monitor all the information coming down, but they also send up that ephemeris information, okay? So the information goes up to the satellite, and the satellite just in turn just grabs it and starts sending it back down. So the receiver itself is, the satellite itself, pardon me, is telling the receiver exactly where it is. Now it doesn't actually report XYZ because again, they're changing so quickly. What it does is it sends basically a positional model. Okay, and this is where we need to understand orbits and orbital dynamics and orbital coordinate systems and all this other fun stuff, which we're going to start introducing here in an upcoming lecture. Well, again, the satellites themselves transmit information to us that allow us to calculate, and now it is actually a prediction if you remember. Okay, we're using the information that we're using is actually a prediction. Okay, so hence the coordinates for the satellites that we use are ultimately also going to be a prediction. We can predict into the future, into the past, however we want with regards to the position of the satellite. Okay, so this information is contained in the satellite's navigation message. If you, again, remember, the nav message was ephemeris, which is like orbital information. It's also information about the satellite's clock. All right, and there's also, I'm just going to say other. There's other information that we will talk about for that. Okay, so in a nutshell, that's how all of these components come together. Now, we're not looking at the mathematics, okay, with regards to, what mathematical formula do I need to use for the observation equations and, things like that. We'll get into that eventually. But now we know that we can determine the satellite's position. We can make range measurements. And then if you believe me, with that information, we can then solve for the position of our receiver. And that's ultimately what we were looking at. How can we solve that? Okay, so now we've discussed all the necessary steps. So selective availability and anti-spoofing. Okay, so we talked about this. So again, selective availability was that intentionally introduced error in the system that restricted non-military users' positional accuracy. All right, it affected their positional accuracy basically by not allowing the user to exactly synchronize, or as best as possible, synchronize with the time in the satellites. Okay, so it was basically, you can think of it that way, that our receiver clock offset, okay, which was again, how does our receiver clock relate to our satellite clock? Okay, selective availability basically kind of factored this, in that the accuracy of our receiver clock would be lower, which means that, right, our delta t, our transit time would be lower. Right, so we times that by C, which means our range estimate would be of lower accuracy, which then ultimately means that our positional estimate, XYZ, is also going to be lower. Okay, and that was called selective availability. It was turned off May 1st, 2000. Again, you saw in the video some pictures of past presidents or current and past presidents signing executive orders and bills and things like that with regards to support of GPS. Okay, so Bill Clinton signed this in 2000 or possibly before, but it was executed May 1st, 2000. Okay, still in place, just set to 0. Now this, I believe this now to be untrue based on my recent reading with regards to satellites. I believe no longer even support the hardware for selective availability. Okay, and then anti-spoofing, as we talked about, which just means again that the P code is encrypted, which means that the civilians then can no longer really, the P code's of no interest because we don't know anything about the encryption. So when, again, an encrypted version of the format of P code is actually public information. We could look it up as to what the structure of the P code is. But again, we don't know the encryption. All right, and the encryption, I believe, changes and things like that. So the P code, when it's encrypted, we call it the Y code. Or sometimes you might see in literature it called the P bracket Y code, just meaning that the P code has been encrypted. P code, unlike the CA code, P code is broadcast on L1 and L2, okay? But like I said, is no longer available for civilian receivers. Authorized receivers can utilize the PA code by knowing the daily crypto keys, which is basically the decryption information that can remove the encryption, okay, from the observed Y code to get back to the P code, which is meaningful, and you can use that information. But again, for us, the civilians, it is not of interest. Okay, so some last things here on GPS management and policies, and then like I said, we'll conclude talking about some other GNSS. As we know, its access is free to all users. All you need to do is buy the hardware. So it's unlike, say, satellite radio, where you need to buy the hardware. So you have, either in your car or in your office or whatever, you need to have the hardware, the satellite radio hardware, but then you also need to subscribe, right, for the monthly fee or the yearly fee that you pay, the subscription fee that you pay for the service. GPS is similar, that you obviously need to buy the hardware, the GPS receiver itself, like your cell phone or whatever, but there is no subscription. Okay, so once you have the hardware, the service is free. The U.S. government will give 10 years notice if GPS is ever to be canceled, but again, as the video says, it's fundamentally a backbone of kind of world economics, right? There's so much business, and right, the way the world works, it wouldn't work the same way today if GPS and other kind of supporting systems were not in place. Okay, so it's extremely unlikely that that would ever be the case. The level of accuracy has been guaranteed, so we talked about in the Standard Positioning Service, or SPS. There's published government documents that guarantee this information. Okay, I can refer to those if you are interested. And the GPS is managed, again, it's designed and operated as a military system. As you saw the gentleman, probably a general or something standing up there receiving the award in his military outfit. It's a military system. It's funded right by as a military system. It's operated by the Department of Defense. However, because of the civilian applications of it, precision ag, recreation, emergency services, all these other things, aviation, all these other things, is that the civilian community, though, does provide input into what's the desire to make this system better, and that is generally channeled through the Department of Transportation, respectively. Okay, so there is still civilian input that's put into GPS. Doesn't mean that it's defined. It's not a civilian-based system, but the civilian users can kind of chime in as to how can the system be better and things like that. So the new signal structures are being developed, as we talked about. So L2C is right on the cusp of being, basically available for everybody, and that's going to change some things substantially. We talked about the L5 frequency, how that's going to be utilized, this new M code, which is, again, no of interest to us. L1C, the interoperability signal between the other systems. Okay, and this is all coming about. And GPS is going to be getting better and better as time progresses. Okay, the kind of financial recession, 2008 and even kind of currently has really kind of impacted this. Okay, I would predict, it's meaningless now, but I would predict that we would be seeing, getting closer to a lot of these today if, the recession and things like that had not happened, but nonetheless. So the GPS market, which is just the civilian market for applications of GPS, like your cell phone, or you buy a car navigation, or all these other applications of GPS, is predicted to have reached about 22 billion. Now, I've read estimates where this number is just continuing to increase and increase and increase. I think I've heard last estimates of over $40 billion is the GPS market. Okay. So again, main market interests include recreation and automobile, positioning and navigation, asset tracking, financial assets, fleet assets, right? I know SAS power trucks are all right outfitted with GPS. I think there's lots of survey company trucks now that are outfitted with GPS just to track where your assets are, where are your crews, where's your truck? Did your truck get stolen? Well, where is it? iPhone with the find my iPhone feature and things like that, right? That's largely facilitated through the use of GPS. Surveying, of course, we'll be spending a lot more time talking about the precise applications of GPS and things of that nature. Okay, and kind of the sky's the limit. Pretty much whatever your brain can brainstorm, GPS is being used in more and more applications each and every day. Okay, so GPS modernization, we watched the excellent little video that talked about it. We've been kind of talking about it, as we've been going through this lecture here today. So there is an official title, the GPS Modernization Program, which is designed to improve the accuracy as well as reliability, security, repeatability of the signals, make them more powerful. Okay, which means that it's our receivers should be receiving a more clear signal, right, less noisy, and all those types of things. Just general improvements all the way around. Okay, so the first improvement again is this L2C that's coming about, which will enable civilian receivers to better account for what's called the ionospheric error, which was attributed to what we'd call that space weather. Okay, how the weather in space can affect positional estimates. It's to be incorporated in 8 Block 2RM and 16 Block 2F satellites. So I think again, we've passed this, which I believe there was 8, if not more, and I remember this number was currently at 9 for Block 2F satellites. Okay, full operational capacity not until at least 2013, and again, I think I created this lecture back when the recession was maybe just happening, wasn't kind of known. So again, this is I would say 2016 onwards before we would reach full operational capacity of L2C. The second improvement will be a CA code on L5, which is that safety of life signal, and that's going to start creating different applications. Okay, L5 is in a very protected frequency domain, which means that there's no other signals that can start encroaching on L5. Okay, in a legal sense, that is. And other benefits. Okay, so again, there needs to be 8 Block 2F satellites apparently that are going to be supporting L5, and then 16 Block 3 satellites, and full operational capacity not at least until 2015. Again, I'd probably slap on another 5+ years, if not more, maybe 5 to 10 years before full operational capacity of basically GPS 3 would be up and about. Okay, and then the third is this application of L1C. Okay, again, these are the civilian implications, not talking about the military, like the M code and things like that. Okay, so again, it's a little bit gray. So these are, every year I basically give this lecture, these dates change all the time, but it's getting closer and closer. It certainly is. It wasn't too long ago where this was, the 10 to 15 year window before these things were going to become a reality. All right, and then lastly, we'll quickly talk about some other GNSS, and I'll supplement this with just some verbal information on some others. So currently there are 2 other GNSS that exist. Okay, now that's not actually correct. I would say that there are 4 actually right now. Okay, so 1 operational, 1 still in testing. So GLONASS is the closest thing to GPS. It's the most developed, okay, to date, which GLONASS is just Russian for Global Navigation Satellite System. That's really what those words mean there. Okay, but we abbreviate it as GLONASS. So it's a Russian system. Again, it's military. It's designed for 24 satellites in 3 orbital planes. So it differs in the fundamental properties of the system, and that GPS has 6, GLONASS has 3. Inclination is 65 degrees, so that's 10 degrees inclined more than GPS. And that largely has to do with, if you look at the geographic nature or the geographic location of Russia as a whole, it's generally further north, okay, higher northern latitudes. They want their system to work better in higher latitudes. So that's why the inclination, which actually lends better to us in Canada, if you think of all of Canada's geography, where we are substantially, have very high latitudes. So for certain applications in Canada, GLONASS can be a major advantage for positional applications. We didn't talk so much about kind of the signal structure of GPS. We're going to talk about that in an upcoming lecture. But to date, GLONASS has a fundamental difference with how it delivers its signals. It's called frequency division multiple access, or FDMA, where GPS is CDMA, or code division multiple access. And again, we'll talk more about that. However, GLONASS is also modernizing, and GLONASS is converting over its new signals to be CDMA as well, which is again supposed to be in line with the interoperability and the sharing of trying to make these independent systems to a degree more common with one another. System has been greatly neglected by the Russians, okay, with kind of the fall of everything over there government-wise and stuff like that. When I was going to university, GLONASS was very actively researched, and if we go back and look at the literature, I apologize, I ended the lecture one or two slides too soon. I think in the late 90s, there was GPS manufacturers that were producing GLONASS and GPS systems. All right, and they would market them. Yeah, it's it can track GLONASS as well, and it's better and this and that. And then when GLONASS started to degrade, all of a sudden the GPS manufacturers just stopped advertising. They were just producing GPS only systems again. And then only recently, when GLONASS started to come back about, our manufacturers starting to advertise it again. So real quick, here's another just kind of overview of the GLONASS satellites, and this number again is old. This number has, I believe it's getting closer to 30, if not more, kind of today with regards to the number of operational satellites. Okay, and then real quick, in the last minute here, there's a couple more. So Galileo, as the video suggested, it's a European one system. Higher satellites, 3 orbital planes. Again, there's some fundamental differences. Long and the short is Galileo is currently being tested. Okay, I think there's currently 4 test satellites that are in orbit. They had an interesting story where 2 of their satellites that were launched together failed to reach their proper orbits. So they are following very untraditional orbits, which make them very difficult to use for positional points of view. So if you want to Google that, it's some interesting reading. Okay, and there's a couple others. China is developing what's called BeiDou, or Compass, as their global navigation satellite system. Japan has their quasi-zenith, and India also has a regional GNSS system. Okay, so sorry, I have a slide here on that. So the Chinese BeiDou system, or Compass, it's planned to be a global navigation satellite system. Okay, I believe there are a handful of BeiDou satellites up. Because China is so kind of closed door, it's tough sometimes to get proper information as to what's happening, with regards to, Chinese space exploration and things of that nature. Okay, and the Japanese have a system called the quasi-zenith system. We'll talk a little bit more about these systems later on, as to how they can be utilized in a multi-constellation sense, or a receiver that supports, 2 or more of these receivers and the benefits that they provide. Okay, so we'll look a little bit more about that coming up. So again, GPS is what we're going to be primarily concentrating on, because it's the most widely used. Though, however, I would say it's pretty safe to say that most modern GPS or GNSS manufacturers will be producing GPS plus GLONASS systems, as well as others coming on board. Right, as more and more satellites for BeiDou get launched and more satellites for quasi-zenith get launched. The manufacturers might start producing other supporting systems. However, for us in North America, like the Japanese system and the Indian system are of no interest because they're regional systems. The satellites only provide information to specific regions. Now that gets a little bit complex with regards to the orbital information. How the satellite's orbit is very different in those systems than how GPS works. But anyways, it's a very interesting time to be, involved in the positional community and satellite positioning, because things are really kind of, every year there's more and more things happening that, it's kind of a game changer as to how, easy our lives can be from a positional point of view and things like that. So it's very interesting, and I very much enjoy teaching this course, and I look forward to our upcoming lectures as well. So with that, I believe that concludes the lecture. These are just some pictures, roughly for scale, just to kind of show you what the core guts of a satellite might look like. Okay, so with respect to the height of an average person. Okay, and so some of these are actual imagery. I believe this is an actual image, and this is an actual image. I think this is GLONASS, and I think this is Beidou. I think this is one of the Chinese satellites. This is artistic, and I think these other ones are just artistic renderings as to what. I think this is an artistic rendering of Galileo as to what it will actually, the satellites will look like. Okay, but again, there's a whole bunch of very complex systems here with multiple antennas, right, for transmitting and receiving, and power supplies, and radiation, radiation hardened so they can withstand being in space, and all these other things in these very, very, very complex systems, which are GPS satellites.